If you've been enjoying 4.1 and 4.2, you're really going to like curve sketching 4.4. We're going to bring it all together. This will be our climactic end to the sections on graphing. I think I mentioned in the previous videos that we'd be moving on to the second half of the chapter and the other idea. Turns out there's this one last section in 4.5 and 4.6. We deal with a different aspect of applications of derivatives. But here in 4.4, we're going to bring it all together: increasing, decreasing, local maxes and mins, concavity, inflection points, and even a little bit more of things that we've done previously in the course are going to help us with curve sketching. So with only seeing the function f of x, we're going to be able to get a really good idea of its graph. So here we go. These are the things that we're going to be looking for. I'll just reveal them all, and looks like they pretty much all fit on one screen. There's just a little bit more here past the bottom. So as you can tell, these are not short problems. For every function, we're going to go through all of these things. So it's 1, 2, 3, 4, 5, 6, 7 different points that we need to hit, information we need to gather. Of course, some of these take very little time, others take quite a bit more. So starting off just by looking at the original function f of x, we'd like to determine the domain, get the x and y intercepts. That will be handy information. And then determine any vertical and horizontal asymptotes. Okay. Then we're going to move on, and using the first derivative, we're going to find intervals of increasing and decreasing. And right off of that, we can get the local maxes and mins. Finally, using the second derivative, we're going to get those intervals of concavity and the inflection points. And these are like the first 3 steps, and then they're kind of broken up into smaller parts. You might want to pause the video and write these down. They are in the book, of course. What I've got off screen here is just the strategy to sketch. So once we have all this information, how do we go and sketch f of x? Well, draw yourself an xy plane. You won't need any graph paper, anything like that. I'm just going to use my white paper, my plain paper, to do that. Draw yourself a nice xy plane and plot all of the points that we found and the asymptotes. So we'll have found, local maxes and mins, x and y intercepts, inflection points, right? Plot those points, plot any asymptotes if there are any asymptotes. And then once we have all those points plotted, those are kind of like the main features. Then we're going to draw our curve through those points, making sure that it fits what we know about increasing, decreasing, and concavity. Okay, let's get into the first example. And yeah, again, these are not short questions. I think my first example here takes about 5 pages. So I'm not sure how long this video is going to go right now. Here's what we're going to do. We're going to sketch the graph of part A, f of x equals x squared over x plus 2. Now, as you're writing that, I'll give you maybe some relief. I only assigned 4 homework questions in this section, obviously because they take quite a bit of time. And it's all kind of recapping things that we've been doing already. We're bringing it all together. So 4 questions. And kind of, I tried to pick, as different styles of graphs as I could. Okay, so let's take a look at f of x equals x squared over x plus 2. If you've got that list of things that we're going to work through, the first one is to determine the domain. So for the domain, I said, well, you know what? Domain, I'm really looking for things that x cannot equal. So x cannot equal 2, because I would divide by 0. So for the domain, I'm simply going to say x cannot equal 2. X is allowed to be anything else. And that's all I'm going to say for the domain. Okay. The next one, the X-Intercept. Okay, so I don't think we've talked specifically about this in this class. So I'm not sure how familiar it is to people to find the x-intercept. Here's the strategy. We're going to set y equal to 0 and solve for x. If you're crossing through the x-axis, then your y-coordinate is 0. So I'm going to take a 0 and put it in right there and solve for x. 0 equals x squared over x plus 2. And so I'm going to I'm going to multiply this denominator over to that side. And I got my answer, x equals 0. So my x-intercept, well, the y-coordinate was 0. I just figured out the x-coordinate was 0. The x-intercept is the origin, 0, 0. Okay. Of course, the next step is the y-intercept, and it's got the opposite instructions. The y-intercept, we would set the x-coordinate to 0 and solve for y, and that usually is a little bit easier because the function's already set up that way. So I'm just going to plug in 0 for my x's and figure out, well, y equals 0. A lot of zeros going on right now. So my y-intercept is the origin as well. Well, if the x-intercept is the origin, then of course the y-intercept would be the origin. Okay, so that happens to be the case for this function, but certainly doesn't have to be true. All right. So those are the first 3 steps. Information that we get just... Oh, my mistake. I almost forgot about the asymptotes. You're probably looking at your list like, wait a second. Don't move on to the derivative yet. Okay, so the vertical asymptotes. Now, this is something that we've done in the class. It was back at the beginning when we were talking about limits and holes and that sort of stuff. And so really there's no real math to do except just observe, hey, x plus 2, that is a factor that did not cancel out, right, from the numerator. So there's a vertical asymptote where this is 0, and it's the same spot that I had to skip in the domain. Makes sense. There's a vertical asymptote at x equals -2. Okay, and then when it comes to the horizontal asymptotes, again, something we did back when we were first talking about limits. What we're going to do, you can ignore this part right here for the moment. I'll just put a very used eraser right there. We're going to take the limit as x approaches infinity for our function. Maybe you remember doing that way back in our first chapter on limits. Now, how do you actually execute this limit as x approaches infinity? You just take the highest powers of x in both numerator and denominator, okay, along with their coefficients, if they had them. So it's like we're kind of like saying, hey, this plus 2, when x gets really, really big, this plus 2 doesn't matter anymore. It's not influential. We're just going to look at the highest powers, and of course this reduces to just x. So if x is approaching infinity, well, then that answer is going to be infinity. How is this helpful graphically? Turns out there's not a horizontal asymptote, but what I can learn is that as x approaches infinity, that was my limit, y approaches this value, which is also infinity. So I guess you could say there's not a horizontal asymptote, but this is good to notice. As x gets bigger, as I go further in the positive direction, the y value gets bigger too. So it's kind of like sweep up and to the right. Hey, we need to take the limit as x approaches -infinity to think about what happens as x goes back the other direction. Well, same idea. We can take the highest powers, simplify, and this answer will be -infinity. So as x approaches -infinity, y approaches that. And now we can say, hey, as x goes back to the left, the y value is going down. So it's going to have this kind of downward thing. Okay. So far, so good. Hopefully I'm not going through this too quickly, since I know you can pause the video and everything. Okay, at this point, we're moving on to the first derivative. And I just went ahead, we've talked, I'm going to assume coming into this chapter that your derivative skills are rock solid. Obviously, that might not be the case, but I'm going to assume that because they need to be rock solid. If you take that original function, what was our original function? Let me write it again. It was x squared over x plus 2. Well, if we need to take a look at the derivative, well, that's a quotient rule, right? So we've got low d high minus high d low all over the low squared. X plus 2 times 2x minus x squared times 1 all over the quantity x plus 2 squared. And I'm going to go ahead and simplify that. So I'm going to multiply out my numerator. Not a whole lot to do there. And I'm going to clean things up just a bit. Not a lot to do in this one. We end up with x squared plus 4x over quantity x plus 2 squared. Okay, so the next two aspects of our graph come from the derivative. What are we going to look at next? Well, intervals of increasing and decreasing. Get rid of that. Okay, so how do we look at intervals of increasing and decreasing? Well, we need to find the critical numbers, and then we may need to make the domain line and that sort of stuff. So we're going to look at where does our derivative equal 0 and where does it not exist. We're going to get answers for both. I'm just going to show you the whole thing since this is really just what we did a couple sections back, nothing new. So when we set the derivative equal to 0, here on the left, I can multiply that denominator over there. Then, in this case, I'm going to can factor out an x. Okay. And then setting both of my factors to 0, I get x equals 0. And from the second one, x equals -4. Okay. On the other side, I'm considering when the derivative does not exist. Well, that would just be when the denominator equals 0. And I get x equals -2. Now at this point, we've seen x equals -2 a few times, right? It was not part of the domain. There's a vertical asymptote there. So it doesn't surprise us that if it's not in the domain and there's a vertical asymptote there, that the derivative will not exist there either. But, you know, the math works out anyway. We don't have to think about it. But it should catch your attention. Okay, so we've got these three critical numbers. So on the next page, I'm going to put those on the domain line. If you remember, the domain is everything except -2, although -2 came out in our criticals anyway. So we've got -4, -2, 0 all marked, making 4 intervals across our domain. So we'll pick a value from each of these intervals and test them in the first derivative. And that will tell us where our original function is increasing or decreasing. So for my first interval, I'm going to pick -5. Hey, you could pick -6 or -10 or -100. Doesn't matter, anything less than -4, plug it into your derivative. And you see me doing that here. I got 0.56. Of course, I don't care what the number is, just the fact that it turned out to be positive. So I'm going to put a nice plus sign there. Okay, then moving on to the next interval. Hey, I'm going to pick -3 right there in the middle. Put that in the derivative, and I got a negative result. So I'm going to put a negative number there. Okay. Continuing in this style, I'll just show you the next two. I'm going to pick -1, and I'm going to pick +1. And I got those numbers to repeat. It's not unusual to have this kind of symmetry, right? We've seen that before. So I got another negative here and a positive there. Okay, now I recommend if you guys want to check, you know, plugging these in, or at least take aware, hey, I'm plugging into the derivative. Yep, because I'm checking increasing, decreasing. That means you plug those numbers into the derivative. Well, with this, we can answer where it's increasing and decreasing. Where I see a plus, it's increasing. Where I see a minus, it's decreasing. And it doesn't quite all fit on the page, so I'll just scroll it down. Here we go. It's increasing from negative infinity to negative 4, and then I jump all the way to 0 to infinity. It's decreasing from negative 4 to negative 2, and then again from negative 2 to 0. Notice that these both, edge up on negative 2, and what is happening at negative 2 itself? There's a vertical asymptote, right? Okay. Again, we don't have to take note of that now, but we're kind of seeing all the pieces sort of start to come together. Okay, so what's next? It's the local maxes and mins. Local maxes and mins. Well, we pretty much done all the work for it. If we go back, I'll go back to our plus minus chart here. Where you change from plus to minus or minus to plus is where you have a local max or a min. So that happened at negative 4. And it also happened at 0. Which one is it here? It went from increasing to decreasing. That's a local max. This one was decreasing then increasing. That's a local min. We don't get anything for negative 2 because it went from decreasing to decreasing. And in fact, there's a vertical asymptote there anyway. But there we got a local max. There we got a local min. It's just a matter of getting the y values. So at negative 4, it's a local max. But what is the y value? Well, we'll plug the negative 4 back into the original function. There it is, x squared over x plus 2. Gives us 16 over negative 2, negative 8. So I've got a local max. And it's just a bit fuzzy on the screen. But it's at negative 4, negative 8. Okay, then we'll also take a look at 0. There was a local min. Well, if I put 0 into the original, 0 squared over 0 plus 2, I got 0. And there at the origin, I've got a local minimum. Hey, that was my x and y intercept as well. Okay. Hey, we're making progress. This video is probably going to go up on the other side of 20 minutes. That's okay. That's the way it is. That's the way it is. Okay, so now we got to take a look. Similar aspect, but for our second derivative. Hey, what was our first derivative? I already forgot. Can you believe that? It's on this other page that I set aside. You're probably like, we know what it is. Oh, yeah. All right. It was x squared plus 4x over x plus 2 squared. That was the first derivative. So to take the second derivative, and it's a bit of a beast because we got to use quotient rule again, but in the midst of that quotient rule, our denominator, when we take the d low, is going to need a chain rule. Well, that's the way it goes. That's just how the rules work. So let's see. I've got low copied, d high, 2x plus 4, minus high, x squared plus 4x, times d low, and there's my chain rule, right? The 2 comes down, drops the power to a 1. I copy the x plus 2. Then I need to multiply by the derivative of the inside, but that derivative is simply 1 from the x, so times 1. And then I'm going to put it all over the low squared, so there's the low, and that's going to get squared a second time. Okay, so I'm just going to clean this up a little bit. There's some work to do, but I'm going to take it one small step at a time. So really didn't even touch these first two sets. I'm not going to start to multiply that out yet. Just going to clean this part up. So I moved the 2 to the first position, and then that and that. And I wrote to the first power here, but I'm gonna leave that off here now. And the times 1, of course. And then our denominator, hey, x plus 2 squared squared is x plus 2 to the 4th, because we would multiply the 2 times 2. Okay. Now it turns out this will simplify a bit before we have to multiply all of that numerator out. Check this out. Each term has x plus 2. X plus 2 squared, x plus 2 to the first, x plus 2 to the fourth. So I'm going to cancel an x plus 2 from each of my 3 parts. So this is going to drop to a third power. And that's going to cancel one of these. And that's going to cancel this whole thing. So I canceled an x plus 2 from each of my 3 parts. It's almost like I factored it out of the numerator and then reduced it here. If that is not clear, hey, let's talk about it in our Zoom session. And I can show you maybe some more steps. But I'm hoping for a lot of people this is very clear. Maybe you wouldn't have seen it yourself, but once I explain it, it makes sense. Now that's going to make our foiling and simplifying the numerator so much easier. Okay, so you can see here I'm just reducing. Okay, so I kind of just repeated what I just wrote. So I've got the x plus 2 to x plus 4 minus 2 x squared plus 4x, and now this is to the third. Okay, so that didn't really do much there. Now let's go for it. We can FOIL, distribute, right? 2x squared plus 4x plus 8 minus 2x squared minus 8x over x plus 2 to the third. And if we clean that up, now this is unusual. I did not expect this to happen when I started the problem or this derivative, but you know, lots of these things cancel out, and all we're left with is 8 over x plus 2 to the third. That is pretty incredible. Worked out well for us. Okay. So now that we have the second derivative, and that was no small feat, we're going to analyze this one, beginning with intervals of concavity. Okay, so I'm just going to show you everything I got here. Now our second derivative simplified so well, there's not a whole lot to solve these. We're going to look at where our second derivative is 0 and where it does not exist. Now take a look at the equal 0. So I'll set it equal to 0. What I did from the second to the third line, I multiplied both sides by that denominator. I multiplied that over here. But if I multiply it, it stays 0, right? 0 times this. And then, but 8 will never equal 0, so there are no solutions here. This does not produce any critical numbers. That second derivative will never equal 0. Kind of interesting. However, it is possible for the second derivative to not exist because we take our denominator, set it equal to 0, and that certainly has a solution. Hey, it's good old x equals negative 2 again. For about the 4th time now. Okay, so what's coming next? We've actually made it to the 5th page in this example. So when I make my domain line for the second derivative, I just mark that one. Just mark that one number. So all we got to do is test a value on either side. I'm going to pick, I'll just show you everything. I'm going to pick negative 3. And I decided to just go ahead and pick 0 for the right side. Why not? When I put in negative 3, I got negative 8 in my second derivative. So I take that negative, right? When I plugged in 0, I got positive 2. So I'll put a big plus sign there. And okay, I can tell where it's concave up and down. Hey, it all fits on the same screen. It's concave up from negative 2 to infinity, concave down, negative infinity to negative 2. So we'll keep that in mind for when we sketch here. Coming up shortly, the last part, inflection points. Now, looking at our line, we're like, oh, negative 2 is an inflection point because it changed concavity. It makes sense to think that, but what's happening at negative 2? Negative 2 is a vertical asymptote. It's not even in the domain. So it can't be an inflection point. Turns out there are not any inflection points here because we, at this point, need to remember that -2 is a vertical asymptote. Now, if we didn't recall that and we tried to plug -2 into the original function, it's going to divide by 0. And so hopefully that at least would tip you off that that something wrong's going on. Okay. Now we're going to bring all this information together to graph. So what I did here at the bottom of the page, I just got it started. So what I did, I drew a nice XY plane, okay? And then I plotted the points that we found. Turns out there were only 2 points. So if you start back in the list of all the things we discovered, we found the X-intercept was the origin, so was the Y-intercept, 0, 0. So I plotted a point there. I think later we found this was a local min. Okay. We also found that the point -4, -8 is a local max. So I plotted a point there. And you can see that I plotted our vertical asymptote at -2. That was pretty early on. Now we also learned that in the horizontal asymptote section that as we go positive here, it's going to go up. And as we go back to -infinity, y is going to go to -infinity as well. We also learned all about the increasing, decreasing, and concavity, of course. So if you look back, and I know I can't put it on the screen at the same time, but we learned, if you look back at increasing, decreasing, we learned that it's increasing from -infinity to -4. Okay, so I'm going to make it increase, and then it's got a local max right there. As soon as you hit -4, then it started to decrease, and it's going to go right up against this vertical asymptote. And so it kind of makes sense. Then it's going to jump to the other side, and we saw in the increasing, decreasing that it decreases from -2 to 0. It's going down. Yet we also know this is a local min. So it's got to be up here and then be coming down to that local min. And it kind of like goes up against if you thought of it going this way. But we always think left to right. It's decreasing until we get to the local min. And then at that point, it increases again. And you might even have it kind of splay, kind of like curve outwards a little, something like that. And then we'll kind of go back. Hey, so it's increasing -infinity to -4. It's increasing 0 to infinity. It's decreasing -4 to -2, decreasing -2 to 0. I've got a local min. I've got a local max. Does the concavity work out? So I've got that here on this page. Concave up, -2 to infinity. Yep, -2 to infinity, it's concave up. It's concave down, -infinity to -2. Yep, it's concave down. Everything checks out. And we got it. That is a really, really good sketch of the graph. Wow, we went almost half an hour on this video. Well, we had all that introduction as well. Let's stop here. We got one more in the next video.